Okay, so here I am in, so hypothesis testing, actually, let me get a new. A simple view of the problem renders the following. That's an interpretation. I want to find a threshold value in my measurements, in my system, that if my measurements, so here are the measurements, so suppose that you have a system that takes measurements anytime you want it, at discrete time instances, or can take them continuously. And you have two conditions, condition 1 and condition 2. You want to be able to know that if the threshold exists, if the measurements exist the threshold, so they fall into this region, then condition 2 is valid and not condition 1. If the measurements are to the left of the threshold, then you have condition 1 and not condition 2. So you divide essentially the region of the measurements, the range of the measurements, in two regions, where depending on the region that the measurement falls, you make a decision. And the decision is a classification decision. You say, if the measurement falls here, you will say condition 2 applies and not condition 1. That's a decision. And why is it a decision? Because you make a decision, but it may be the wrong decision. It happens many times in life. That guy is against me. That's a decision. But that guy may not be against you. That might be purely in your own mind. Someone is after me. That can be delusional. That's psychosis, actually. It's an interpretation of a measurement that never exists in the first place. The brain creates a measurement. But the brain then is led to a decision which is not exactly the true decision. It doesn't match the truth. Decisions are always true because you make them. They are facts. You react based on those decisions. But those decisions do not necessarily match the true nature, the true state of the nature. And what do I mean by the state of the nature? State of nature. This is a term we use in classification theory. State of nature means objective assignment of class. I present to you two fish, and suppose that you are an expert of fish. You can tell that one is a salmon and the other is a sea bass. Suppose that I hold those two types of fish. You can distinguish them based on objective criteria. Now, you give those two fish to somebody else who doesn't know a lot about fish, and say, well, you know what, I can just choose at random. Say, this is salmon. Because he doesn't know what salmon looks like. He knows them only by the tag. He can recognize, that individual can recognize salmon, any salmon in the fish market because it carries a tag. It says salmon, sea bass, halibut. Doesn't have to know. Somebody else did the recognition. But the classification already exists. And class assignments are called in general states of nature. So in hypothesis testing, essentially we have a class assignment. And that class assignment is formulated by the hypothesis. And it's determined a hypothesis. And the hypothesis in statistics has a more mathematical formulation. It has, you can write some equation to define the class. Okay? So the situation is the following. I have a random variable x. Here's the description of the problem. And I know, suppose that you know the type of the distribution of x. In general, that is okay, or you can have some other assumption that can essentially replace that. But you know that all this random variable x is going to be from one type of distribution. Even if you don't know that type of distribution, you know that it's coming from one type of distribution. So for simplification, let's forget that you may not know the type of the distribution. Let's assume that there is an oracle that always tells you beforehand what is the type of the distribution. It's a magic right now, okay? Divine power. What you don't know is a parameter that determines the distribution. Suppose that we're interested only in one parameter. In one parameter which I call theta. I use this Greek letter which is called theta in Greek. Not theta, theta. I don't know what should be the proper phonetic here, but let's not worry about that. And now you come back to connect the problem as I did it before. You take some measurements. And in statistics, what are the measurements? You try to find a random sample and extract measurements, take measurements from the random sample. Those are your measurements. And then using those measurements, you cook a statistic. And that's your final measurement. And you always say, if the value of the statistic, the value of the measurement is greater than the threshold, I say that my distribution, my random variable x has distribution which falls in condition 2. If my measurements fall into left of the threshold, then you would say that my random variable x has a parameter theta whose value doesn't fall into condition 1, but it falls into condition 2, into the range. Let's call the range of values of theta to be condition 2. This is pretty much the hypothesis testing problem. Now, why did I say that here? And suddenly, when we're talking a problem, when we're discussing this problem that we had before with the men and the women, I made this particular jump to hypothesis testing. Because as you will see, as we do with parameter estimation, with estimation of the difference between means, this is a critical condition. It's too important to be ignored. And I can illustrate why it's too important to be ignored. This problem again reappears in hypothesis testing. What is happening? If you have two means, let's say the mean of women, let's say X again, which was the resting pulse rate of women, is okay. Let's put the women here. They were Y. Here is men X. If they're just like this, nice normal distribution, and this is their mean here, and men are slightly bigger, slightly higher, slightly No, actually, this should be men. Men have a smaller resting pulse than women. Actually, and this is women here. You see what I did here? When I go to women, the standard deviation is practically this distance. And with men, it's this distance. So this is the situation when you have unequal standard deviations. When the standard deviations are unequal, then and you are in the awkward position that these two, the difference between the mean of x and the mean of y is small, then it's very hard to distinguish those two curves because one is sitting on top of the other. So this would be a serious problem here in what we discussed before, in the example between men and women, the confidence interval estimation. The problem was asking you to estimate this distance here. In hypothesis testing, as I will show you, we always we do have a similar situation, but we can only draw an analog from what we will talk there to apply it here. But essentially, you are making a device, you are making something that takes measurements, and you're trying to compare, to estimate the difference between the two means. If you are in the particular situation that you have here, then you need big samples to be able to understand, to feel the difference. For example, from one sample, you can't feel the difference. Take one man and one woman, you can't feel the difference between the two. Because very likely, the woman's range can be anywhere here, and the man's range could be anywhere. Curves disappeared, I'm sorry about that. Could be anywhere here, where you said. So, just by one measurement, by a few measurements, since the two curves were overlapping a lot, the measurements could be very dicey. But if they don't overlap a lot, now I can go to the means. The mean of x bar and the mean of xy, since we have the central limit theorem, are much more compact than that. The curves are much smaller because the standard deviations are now divided by the square root of 200, which is a big number. And although this is like this, then now you see that the curves for the means, the curves, those are called sampling distributions, okay? Those are the PDFs of the sampling distributions. Of x and y. Those sampling distributions now have curves that are far apart from one another. You don't have the previous awkward situation. Why is this happening? Because you took a very big sample. So when we suspect that the means are kind of close, as it can be with resting pulses of men and women, both are humans, so they're not going to have that big of a difference. And you don't know the variances, then you have to take big samples. Otherwise, you're not in this good situation where the two curves sit far apart from one another, and your estimation is quite clear. It's much easier to be done. The curves sit really one on top of the other, and this is one of the biggest problems in artificial intelligence. This is exactly the inability to classify. Because the two curves, the one that describes condition 1 and the one that describes condition 2, are sitting one on top of the other. So you have a big overlap, and when you have a big overlap, it's legitimate to say, I'm in condition 2 and I'm in condition 1. Both are highly probable. So you're better as well just flip the coin. You have no way to decide. You have no threshold. And in this case, you need more measurements. If you take more measurements, then the threshold can easily be defined. And as I will show you later, actually immediately, the threshold can be set. Okay? Right in the middle. That would be a nice threshold. So let's go back to the hypothesis testing. That happens with probability 0, because you have continuous random variables. So there is nothing exact in that. Okay? So what is the problem of hypothesis testing? As we said, we're interested in one parameter theta. And we want to be able to classify x, the random variable of whom the distribution, let's say that we know, according to what is this parameter theta. I can give you some very easy examples. Let's go back to the men and women that we had in the problem, in the homework problem. And then x, you would say that one situation would be, do men and women have the same resting pulses in average? That's one question that you can formulate. When you look at when you actually looked at the data that I gave you, with the neuroscience data set from the adolescents that had schizophrenia, and they measured the cerebrospinal fluid volume. The question would be, in terms of the hypothesis, I don't know what is the distribution of this random variable, volume of cerebrospinal fluid in humans, but the question would be, do adolescents with expressed schizophrenia have a smaller volume in average than their normal counterparts, the non-schizophrenic counterparts? That's a hypothesis testing question. You are formulating a hypothesis. And in this case, you would ask, is the mean of x equal to a set value, or is the mean of x greater than this value? Is the mean of x less than or equal than this threshold value, mean sub 0, or greater than that? So this is called hypothesis 0. This is called hypothesis 1, or alternative hypothesis. And when we set scientific problems of this kind, we always look at the alternative hypothesis. The statement that you will formulate as a researcher is always the alternative hypothesis. This hypothesis called H sub 0 is called null hypothesis. And the null hypothesis is an auxiliary hypothesis. It's an auxiliary hypothesis because you only use it to set the solution of the problem. Okay? So let me set the solution of the problem. Let's see what are the mechanics of solving the hypothesis testing. And now you will also understand what I'm talking about decisions, about the classification decisions, and about the errors that can possibly occur. So suppose that I have x, my random variable, and what I don't know about x is whether its mean exceeds this value, m sub 0, or it's greater, or it's less than or equal than m sub 0. When you formulate, one remark, when you formulate your null hypothesis, although technically it's nice to be formulated with m sub x less than or equal than 0, for the technical reasons which I will explain, will always be formulated with equality. So you will always use the equality. Why? Because that, mi sub 0 is exactly the dividing line between condition 1 and condition 2. Condition 2 is what I would call the alternative. Condition 1 is the null hypothesis. This is condition 2, and this is condition 1. And now you want to know whether the means of x that determine that you're interested in exceed this value, or they're less than or equal than this value. So now you start setting the problem. Suppose this problem is being set in the following way. It's reminiscent a little bit of, so I do x to have the mean x sub 0, and suppose that x has a nice normal distribution. Let me put the tails a little bit high because I will need them. And I'll give the bell a little bit of breath. Okay, so here is mi sub 0. So my first step is to assume that the mean of x is equal to mi sub 0. That's the null hypothesis. If this is true, how do the data position themselves? How do the data fit in what I have discovered, I have assumed? That's exactly the problem, the actual procedure of solving a problem of hypothesis testing. So we're testing for a mean here, and of course, again, the big toolkit, our DNA in mathematics, or actually what the DNA would be for criminal procedures, the DNA investigation in mathematics is the central limit theorem, statistics. What I would take is, take x bar, which comes from the data, and now you have x bar, and you try to see where x bar fits with respect to the assumption about the data. And that really puts you to another picture. It puts you to another picture because I need space here. So now we take x bar. That's supposed to be a straight line. It's not very straight. Let's make it straight. That's better. What is going to be the sampling, the PDF of the sampling distribution of x bar, if this is the PDF, the curve of the PDF of the sampling distribution of x, is going to be more compact, okay? Why? Because x bar is a sampling distribution whose standard deviation is the standard deviation of x divided by the square root of the sample. So it's always more compact. What is going to be the mean of x bar? You assumed that the husband is the assassin. You assumed that the mean of x is mi sub 0. So what is going to be the mean of x bar? Somebody? Mi sub 0, yes. mathematically speaking, the mean of x bar is the mean of the random variable. That's what we proved. And this is equal to mu sub 0. So you expect to see this for x bar. Something like this, yeah. But now that variance is sigma over the square root of n, where n is the sample size and sigma is the standard deviation of n. Okay? So this is where this is what I expect to see. This is the sampling distribution here. Of x bar if the mean is equal to mu sub 0. That's what you would expect to see. But if you don't see that, but instead you see that your x bar is positioning himself somewhere there, somewhere further from mu sub 0, suppose that x bar, you put x bar now and the value comes here. What would you think? It seems that, yes, I made this assumption, but when I try to put the husband at the scene of the murder, doesn't seem to know what would happen. So that can't be the culprit. If x bar is here, it's kind of unlikely or way less likely to be coming from a distribution that has mean equal to mu sub 0. What has happened here? Why do you say that? You say that because this number fits now at the tail of the distribution. That's exactly the key. That mechanism is the key of understanding what is hypothesis testing and how hypothesis testing works. Okay, now I need to formalize that procedure. I can't have that procedure being intuitive. I have to formalize. And moreover, I want to make a formal determination of what is my probability of error. Suppose that I made an error of judgment. Suppose that I took the measurements, I fit them on the graph, as I did here, and based on that I say, well, the mean doesn't appear to be equal to mu sub 0 or less than mu sub 0. It appears to be greater than mu sub 0. When I say the mean appears to be greater than mu sub 0, based on this picture here, I make a decision about the state of the nature. The mean is what it is. What I do is to make a decision about what the mean is. If that decision is correct, then you have the correct culprit. If that decision is wrong, then you kill the wrong person. You sentence the wrong person. That's exactly what happens. It's a decision. It's like a court ruling. In the court, you don't necessarily find the truth. You make a decision about what you believe it is the truth. And hopefully you want to make that decision with the highest reliability. Okay? It's exactly the same procedure. It's exactly the same analysis. Now, of course, in courts you will never calculate that probability, and we've seen situations that the opposite happened. Not very often, hopefully, thanks God, actually. But here we want also to find a way to understand this procedure mathematically, to quantify the level of our certainty in this decision making. So that's the question now. Quantify the certainty in this decision making. Okay, now let's describe the decision making. Graphically. So I will make a graph here. Second part of this talk. And what we want to see is, I want to draw some conclusions about the problem of type 1 and type 2 errors from false positives, the concept of false positives and false negatives, because this is a problem of discriminability in general. Actually, when we started earlier today, we mentioned that the same problem we also have when we deal with confidence interval estimation. So let's see what is the problem of discriminability in general. I will do a very simple case where I will try to find a threshold, to consider what I call a threshold. So I have class 1 and class 2. So I have two states of nature, and those are defined by an object belongs to class 1 or an object belongs to class 2. And every object will belong either to class 1 or to class 2. There's no intermediate case. So the universe splits into classes, class 1 and class 2. Those are the states of nature. And now I have a measuring device which measures a quantity. So the measuring device, a sensor, measures a quantity. And this quantity measures a quantity which I would call Q here. I will denote by Q. It's a measurement, something that I will measure it. Now, the problem is find a decision rule. The decision rule comes here also in the hypothesis testing, and the decision rule here is find a way to say I accept the null hypothesis or I reject the null hypothesis. The same here, you want to make a decision. The decision is an item belongs to class 1 or to class 2. And to derive that decision, you have to have a decision rule. And the decision rule will be of the form, since you take only one measurement, the measurement Q, if Q is greater than a certain value T, which I would call threshold, then I have to see how I can find this threshold, greater than or equal than Q, then the item belongs to class 2. Otherwise, item belongs to class 1. This is the decision rule. So as we say, on this axis, on the horizontal axis where we mark the values of Q, we will have two decision areas, an acceptance and a rejection area. So if a value of Q falls within what we will call rejection area, we will say that the item belongs to class C2. Otherwise, the item belongs to class C1. So we need to place the threshold T. The threshold T is the boundary of the two areas. So let's say that we place the threshold T here. Then this you can call rejection. That's more compatible with the hypothesis testing. Rejection region. And this is acceptance region. And this actually choice corresponds to class 1, or so we hope, and class 2. So this is the parallel you should draw. for the two classes. Okay. Now let's see what is the optimal way to find the threshold here. And by the way, what I'm describing here is to find a very simple classifier which is based on the threshold. And what I'm supposed to know in order to find this classifier is the PDFs, the probability density functions of the Q value. So I have a random variable which I call Q. That's a random variable. And it's the random value of my measurements. And based on this, the values of this random variable, I draw the decision whether an item belongs to class 1 or to class 2. Now, the PDF of the values of Q, if an item belongs to class 1, is the first curve, the curve that we mark here. And the curve of the PDF for the Q values, if the item belongs to class 2, is here. So if I want to make a more precise statement, I would say that this is the PDF of the conditional, this is the graph of the PDF of the density function of the conditional distribution of the values of Q given that the item belongs to class 1, and this is the graph. The right one is the graph of the PDF of the conditional PDF of Q given that an item belongs to class 2. And those are called priors. Those are prior probabilities, and typically we learn them in a phase which is called training. We go out and we collect the measurements and we conduct a statistical study, and from this statistical study we know that the items, we know what the values Q, or we can estimate, let's say, confidence intervals, or more precisely tolerance intervals for the values of Q. So this is something which is called training, and it's done with some statistical study, or if we cannot have the parametric model that I'm describing here, then we do the study with machine learning techniques, and here there are several techniques that can be used. Probably the most known one is Bayesian, is support vector machines, but of course there are many other techniques like ADA boosting. Anyway, beyond the topic, beyond the goal of our little investigation here. So, if I wanted to make this even a bit more formal, I would say what I put here is class 2. I would replace the condition with a random variable, which I would say takes the value 2. X, that random variable, takes the value 2 if the item belongs to class 2, and it takes the value 1 if the item belongs to class 1. And that X would be, as we call, a Bernoulli random variable, or more generally, a categorical random variable. And X is referred to as categorical. To class 1. Otherwise, X is equal to 2. So you can think of X as a flag or something, or a tag. So in general, X is a Bernoulli random variable, but if more generally, I would refer to X as categorical random variable. It's a categorical random variable because X, the values of X indicate classification, indicate class assignment. That's why we call it categorical random variable. Now, let's see, if we put, let's say that I pick T here. I pick that particular threshold that I have marked. Let's draw the vertical line all the way up. I'm interested in the misclassification. And the misclassification cases are the following. An item belongs to class 1, but I classified it as if it belongs to class 2. What would that be? That would be exactly the type 1 error, because if I say that an item, it's like hypothesis testing, I can say that the null hypothesis that the item belongs to class 1, then the alternative is that the item belongs to class 2, because there is no other way that an item either will belong to class 1 or to class 2. So the type 1 error would be for an item, although it belongs to class 1, to be classified as class 2. So in this case, that means the probability, what I want to find out is the probability that item is classified as class 2. So essentially, I'm finding this probability. Q is classified, the decision rule. The classification is done by the decision rule. Decision rule gives that Q is greater than T. So let's write Q greater than T, given that X is equal to 1. So class 1 that's what that means. And this is exactly the probability of the type 1 error. That's essentially the significance. And I will tell you exactly what the significance is. Let's look at this probability. What are we going to look? The condition is X is equal to 1. But if we look here at our graph, the first of the left of the two curves is the one that actually corresponds to the graph of the PDF when the class assignment, the graph of the PDF of the values of Q, of the measurement, when X is equal to 1. And since the condition, the rule says the value of Q should be greater than T, what actually I should be picking is this area. When the values of Q are greater than T, then they right to the right of T, but the probability that this occurs given that an item belongs to class 1 is exactly equal to the area, which is now marked by yellow. And this area is called critical area because it's to the right of our threshold. Okay, and let's see, I would call this critical area or critical region. So this is called here critical region. So that would give me a certain value. And I will call this value equal to A, and this is the area which is now marked with yellow. Now let's continue and go to the other misclassification. The other misclassification is an item to be classified of class 1 although it is of class 2. When an item is going to be classified of class 1, let's look at the decision rule. That means that Q is less than or equal than the threshold, given that the item is of class 2. Let's see what that probability would be. I would call this probability equal to beta, to B. That's the Greek letter beta. And not beta, beta. That's correct phonetic for this letter. You actually know it sometimes like beta, but it's not correct. We don't call it beta in Greek. Let's see what that vita would be, that quantity. How am I going to calculate that quantity? Let's take now the blue. Now, the value of Q is to the left of T. So it should be somewhere here. So here is the value comes within the so-called acceptance region, not at the rejection region or critical region. Rejection and critical are the same. But we know that the item is of class 2. So what is the probability that the item is giving a value of Q which is less than the threshold, although the item, given that the item is of class 2? Well, it's the area which now we mark with blue. It's an area under the second curve, the one to the right. So if we put our numbers, so this area is equal to beta, the blue area, and this area is equal to alpha, the yellow area. So if we go here, this is the area which is blue. And one of the two represents the false positive and the other represents the false negative. So if I say that I want to if we do an example and we say that if the value of T is less than a certain, the value of Q is less than the certain threshold T, we consider that the patient, let's suppose that a patient has a condition which is now identified as class 1, then if you classify them as class 2, then you have a false negative, because the patient doesn't have the sought condition, which is class 1. Otherwise, if the patient falls in the acceptance region, but is a patient who belongs to class 2, then the patient then that would be the false positive. But of course, you can reverse these two things. So these probabilities, this is a type 1 exactly error, and this is a type 2 error. And you can associate, if you associate this with false positive, then this definitely is associated with false negative. But the associations of false positive and false negative can be changed, because it depends on what would you define as positive. It's a matter of definition and not a matter of, it's a matter of convention, not a matter of absolute truth. It's how you see things. So here, let's see that situation. Let's see our situation now in the graph, as it is described in our graph. As you see, the yellow area is much smaller than the blue. And if I say that the yellow area is the false positive and the blue area is the false negative, then it depends what I mostly want to live with, okay? So if for example, you don't want to have false negatives, you have like an HIV test that you don't want to have false negatives, what would you like to do? What would you like to do is to make the blue area smaller. So you wouldn't pick T there where you have it, but you would pick it probably here, and you're more likely, you would move T to the left. You will draw the threshold to the left to reduce the false negative rate. Whereas if you draw T to the right, you reduce the false positive rate, but you increase the false negative rate. And this is exactly something that actually happens in type 1 and type 2 classification. and this can be marked, this can be actually illustrated graphically with a curve which is called operating characteristic curve. We'll see how it's been marked on the curve. Now, the type 1 and the type 2 errors, or the false negative rate and the false positive rate, as you see, they can be, you can make one bigger, you can make the other smaller, you can play by just moving the threshold t to the left or to the right. If you move the threshold t to the right, you will make the false positive rate smaller, but you will increase the false negative rate a lot. Now, there is some sort of an optimal balance between the two, but there is no way that you can minimize both. You can have both equal to 0. That's impossible, as you see from this graph, because when you make one smaller, the other becomes bigger and vice versa. This is because the two curves overlap. However, the best balancing position is this particular here. Because if you put your threshold at this particular point, t prime, then what you notice is that both areas become somewhat balanced. Both the false positive and the false negative. Here you have, as we say, the best trade-off. But this may not be very realistic. What is realistic is what your application demands. If the cost of having significant false positive is very high, then you have to live with false negatives. If the cost of having false negatives is very high, then you have to live with false positives, and this is how, depending on what this cost is, to determine how you pick t, how you pick your threshold t. So a very analogous case is exactly here when we do hypothesis testing. When we say, is the mean, when we make the hypothesis and we test, let's go back, let's scroll up, is the mean greater, the mean of x, the random variable x. Now, I'm not talking about the x that I had before. I'm done with this example. If the mean of the random variable x is greater than a set value, or is the mean equal or less than a set value. That's exactly a problem which is similar to what I had here, because we have, again, the state of nature. That mean can be greater than mu sub 0, it can be less than mu sub 0, and then, but we have to decide for what is the class, what is the state of nature. Whether the null hypothesis is correct or the null hypothesis is not correct, and therefore the alternative is correct. We have to make a decision. And once again, the decision is based on a rule that now we're going to define. So here is design of hypothesis testing for means. I will do the very simple test. And you will see some more in the next video. So we take x bar, and the reason for which we take x bar is the sampling distribution of x bar. The sampling distribution of x bar as a variance which is much smaller than the variance of the initial population. So let's say that this is the PDF of X bar, of the sampling distribution. The characteristics are that the mean of the sampling distribution is equal to the mean of the random variable X, for which I'm testing my hypothesis, and the sample standard deviation, the standard deviation of X bar is equal to the standard deviation of X divided by the square root of N. Now, to understand the critical region, let me just scroll back for a second here and add to my example before and add something. Suppose that the two means Q1 and Q2 that I had here are not that far apart, but they're much closer. So if you have one area overlapping the other, let me show it here a bit. If you had this condition, that's the area for Q1 and that's the area for Q2. And they do this. The means are very close. If you select your threshold here, let's say, then you have a small type 1 error, but you have a very big type 2 error. What is going to be your type 2 error? Your false negative. This is going to be here. All of this curve in accordance to what we had here. So that's my blue and that's my yellow area. If you pull the threshold, if you try to have a smaller false negative, false positive rate, false negative rate, and you move the threshold to the left and you put it here, then essentially both errors are going to be big, because still that would be now your new yellow area, and this is going to be your new blue area here. And what does this thing say? It says that if the values, if the PDFs of the priors do not have some discriminability because their means are very close to one another, then it's very hard to make the threshold to work. I will have something, but I will have to deal with very high false positives and very high false negative rates. This is exactly what is happening with the mean as well. But with the mean, the central limit theorem is telling us this, that the sampling distribution of X bar is approximately going to be normal distribution, hence the bell that I designed, and the standard deviation is actually being reduced by the size of the sample. So if I have a difficult problem, if I pretty much believe that it's hard to test my hypothesis because there is because there's not enough discriminability, then what I can do is to increase the sample size. We'll see that a little bit now as we continue. So I'm taking this, and now I want to define a region. I want to define what is called significance. So the significance level is the probability of the type 1 error. This probability is conditional. So as we mentioned, when you construct a problem, you assume that the random variable x has mean equal to me sub 0, so that should be equal to the mean of x bar. You assume that. If this is true, then the measurements should be the measurements of x bar that you have obtained from your random sample should be mostly lie close to m sub 0. Therefore, you can say, if I want to control my error, my type 1 error, I cannot live with more than a error. I find a value here which says, I would call this to be critical value, and that critical value will be defined by the following. This area, which now is going to be my yellow area, and I choose yellow in accordance to what I've chosen before in the previous example. This area is called here, this region is called critical region, and this value to the right of this obeying this value is called critical value. Remember what I wanted to test. I'm testing a hypothesis where it says the mean of x is less than or equal than m sub 0, and of course we work with the equal, not with the less. Against the alternative, which is it has to be always the opposite statement from the null, the mean of x is greater than me sub 0. This is called one-sided test, and in particular this is a right tail test, because the yellow area that you see here is to the right part of the curve. This is the acceptance. So if I do my measurements, if I take my measurements, my sample, my random sample x, and then my measurement is going to be the value of x bar, then I see if x bar belongs to the right of this critical value, which I need to find. I need this area, it was not correct that I put this above. This area should be, we will calculate it. Now we'll find what this value is. I want to the right of this value, the area, the yellow, to be equal with yellow to be equal to A. And of course, what remains under the curve now is equal to 1 minus A. So that means that this is my probability of type 1 error, because what is the assumption? The assumption is that the mean of x is equal to me sub 0. That's why I call it type 1 error. Type 1 error is the error where you reject the null hypothesis, although the null is true. To reject the null, you have to be to the right of this critical value, which is yet to be determined. Okay, now let's find the value. We want x bar to be greater than this value, which we're going to find. Let's call this value, let's give it a lowercase x, so that this probability is equal to A, so the probability that x bar is less than or equal than A, than lowercase x, is equal to 1 minus alpha. Alpha is called significance. And it's called significance. Well, let's do this calculation, then we'll say why it's called significance. What we do is what we did with confidence interval. Subtract the mean, the alleged mean, which is me sub 0, divide by the sample standard deviation. So you divide by the standard deviation of the sampling distribution, which is sigma divided by the square root of n. And now all this has normal distribution. Of course, you do that both sides. For the time being, we assume that we know sigma. I don't want to have to deal with the technicality that of not knowing sigma. Let's assume that we know sigma. Then this quantity, which says that if I'm to the left, to the right of x, or if I'm to the left of x, I accept, so this is acceptance. Exactly, this inequality means acceptance. This inequality means rejection. Boils down to this rule here. But since this quantity is approximately normally distributed by the central limit theorem, when n is sufficiently big, let's say bigger than 30, then x bar, when it's standardized, has approximate standard normal distribution, because x bar has normal distribution with which parameters? This mean and this standard deviation. So now I found the value that I want. This value should be the value that should be equal to z sub a. This is the 8th quantile of the standard normal distribution. And it's exactly the number that if you plug into the distribution function of the standard normal will give you probability equal to 1 minus a. You find that from the table. So now the problem becomes completely algebraic, the problem of finding x. So x would be equal to this mi sub 0 times. So the decision rule is the following: x less than or equal than h sub 0 is accepted. Otherwise, h sub 0 is rejected, and if h sub 0 is rejected, you accept the alternative hypothesis. This is a very easy way to get this particular one-sided, as we call it, right tail hypothesis testing. And we designed this test by essentially selecting, we customize the test so that the type 1 error is not going to exceed this quantity alpha. Now let's see what the beta is going to be. Now I want to see how I can calculate the type 2 error. Well, the type 2 error is not it's not an absolute value. It's something that actually depends on what the mean is. So when we have type 2, we have type 2 error if the mean of x, based on what we're doing now, on the fact that we're doing a one-sided what we call a right tail test. This was a right tail test because the critical region is to the right. And based on that, we also take the type 2 error. We take the nature of the type 2 error. So we make a type 2 error if we reject if we reject the alternative hypothesis, which means we accept the null hypothesis, although the mean so I put when the mean of x is greater than mi sub 0. Well, there are many values for the mean to be greater than mi sub 0. So what we actually do now here to be able to begin assessing that error is to take a value for the mean of x which is greater than mi sub 0. So let's see. The sampling distribution for the mean will be this, for x bar. So this is the PDF of x bar under the assumption that the mean is equal to mi sub 0. So you see it's centered here. And let's say that we have a bigger mean. That indeed the mean of x is equal to mi sub 1. So the truth, as we tell, the true state of nature is the following. The mean of x is equal to mi sub 1. And as you see here, mi sub 1 is greater than mi sub 0. And now here where actually the true PDF of x bar is. So that's the true PDF of x bar. This is the alleged, this one here is the alleged PDF. Alleged because you operate, when you do this design of the solution, you operate based on the premise that the mean of x is equal to mi sub 0. You ignore the fact in your design that the mean is something else. Now you want to see what happens in what is the probability that we accept h sub 0, that's the type 2 error, given that the mean of x is equal to this particular value mi sub 1. Okay, now of course if we want to find the type 2 error, the type 2 error is more general. It involves more values, more possible values for the mean of x, so it's more complicated. I don't want to discuss it in its greatest generality. But here, what you see is the situation. This should ring a bell. It's the situation we saw before in the discriminability. That's exactly what we have. So our critical region is basically defined based on that test, and let's say that here is our critical region. Let's say that this was our critical region. So here is the critical value, which we mentioned that in this particular case, in the right tail test, was this. So what is since this is the right tail test, since I took this to be the critical value, what should be now the type 2 error? Well, the type 2 error is, since we say that we accept h sub 0, what is the value of x bar that we observe? The value of x bar that we observe should be here. So what is the probability that we accept h sub 0? We accept h sub 0, that means x bar is less than or equal than critical value, which we mention what the critical value is, given that the mean of x is equal to mi sub 1. Well, since the mean of x is equal to mi sub 1, we don't take the alleged curve. We forget the alleged curve. We take the right curve. My dogs are just gone crazy. So this is the right one, the curve that I draw that I mark actually with the blue is the true curve for x bar. And as you see, based on the acceptance region, this is the area of whom the probability represents this particular probability. So that probability is equal to the blue area that I said it. And this is actually, I would call then, the notation that I will use is vita, and I will put in parentheses, made the parentheses too big, mi sub 1. And as you see, it's a big error. And it's a big error. Why is it a big error? It's a big error because the two curves are close. If the two curves were further apart, then it wouldn't have been the error wouldn't have been such a big error, because then what would have happened is that if the two curves were tighter, let's see, actually this is very, very important to mark. Let's see that we have tighter curves. So they would be like this. Actually would be go a little bit up over that, but that's not a problem if they were like this. What would have happened is that when they are tighter and with the same values, true value of mean of x is equal to mi sub 1, the critical region would have moved here, the critical point. And as a result, that would have given a smaller value for beta. It would have reduced the value of beta. How can I take these curves tighter? How can I make this nice situation, which was the situation that I had here when I first spoke about discriminability? I can do that by increasing the sample size. So when mi sub x is equal to mi sub 1, if you want to hedge against the type 2 error, then the only way you can reduce it is for values of the mean, of the true mean, which are close to mi sub 0, is to reduce it, to increase the sample size. So, in other words, to reduce beta mi sub 1, we must increase the sample size. And this is exactly what we said with discriminability. By reducing the sample size, we reduce the discriminability between the discriminability of the statistic x bar. Now, the last concept that I have to talk about is the operating characteristic curve. To understand how the test works, we create a function, we create a curve, which is called operating characteristic curve. And this operating characteristic curve is the graph of a function, the function beta, the power of the test, given that the true mean of x is a value mi, which belongs to the range of the possible values of mi, the possible values of the mean of x, given that the alternative hypothesis is true. So in the test that I'm presented here, the alternative hypothesis is that mi is greater, the mean of x is greater than mi sub 0, so we'll take that interval of possible values for the mean of x to be the interval which lies to the right of mi sub 0. Well, let's see what is the situation of, what is the probability of accepting h sub 0 when a value of the mean of x is close to the mean mi sub 0. Or let's see, when actually we have the situation that this value mi sub 1 moves, starts getting closer and closer to mi sub 0. When this happens, the two curves, one fall on top of the other. So what is now the blue region? The blue region will not be here where it is, but imagine this shifted to the left, but see here you have your threshold, here where you had your threshold, okay? That particular point, the red point here, that's where the threshold is. That threshold stays, of course, over there, but now the true curve is very close to the other. So the blue region, because it's the acceptance, is almost equal to the entire to the entire curve. What is missing? The part that would be missing is exactly the alpha. So you will see this going up. I did it almost nicely, but not all the way too nicely. So at mi sub 0, this probability beta, very close to it, will top, and what will be left is this alpha, the level of significance, the level of statistical significance that the test has. That's why we call it statistical significance, which means, can I discriminate things? What's my power of discriminating things? If the value of the mean is what it is, is the sample good enough that actually gives me some ability to make an assessment, to make a statistical assessment? So is the sample significant enough? That's why to lead to some conclusion. That's why we call alpha to be the significance level. So that will also be analyzed more on the other video. But what I want to tell you here is that the operating characteristic curve in this particular test would look like this, and it's the curve that actually is the graph of the values of beta, of mi, which is this probability, when mi ranges in values greater than mi. And of course, depending on what type of test we do, this also changes. In the next video, you will see also some examples where you can actually calculate these values. With this, we conclude. To see to use the confidence intervals, I want to do two more things. We have the confidence intervals here. That's the homework that you did, and I would like to use the same homework, the very same homework, to develop some problems for hypothesis testing. So let's look at problem number 1. Random samples of 200 men and 200 women were collected, and their resting pulse rates were measured to estimate how much mean resting pulse rates differ from between men and women in the population. Forget what the rest does, the rest of the problem says. What is the problem here that we have to test? Here is whether the hypothesis that we're formulating is that the mean, you see how much mean? You see that statement here? Mean means average, means mathematical mean, means expectation. Here we have two random variables, x and y, and in this random, and between those two random variables, the hypothesis would be if men have higher mean rate than women. That would be the H1. That's the hypothesis I want to test. The hypothesis I want to test always will lead you to the formulation of H1. Now, what would be the null hypothesis? The null hypothesis would be that the two means are the same. The null hypothesis is an experimental, is an auxiliary statement. It's an auxiliary statement which you use only to design your problem. to the mean of women. So that would be for the first problem. And since I want to test that one mean is greater than the other, that would be a one-tailed test. But here it involves two random variables, so I would do the difference of two means, and this is something that you will see in the next video. Now let's look at problem number 4. The heights of a random sample of 100 women are recorded. The sample mean is this, and the standard deviation. Here I can form a problem and say, do women heights exceed, let's say, 66 inches in average? If I say in average, the use of the term in average means automatically mathematical mean. So if I'm asking the question, do women heights exceed 66 inches in average, that's a hypothesis. It is exactly the alternative hypothesis. What that would be? Mean of x greater than 66 inches. What that is? That's h1. What then would be h sub 0? H sub 0 would be the same statement where instead of the inequality you have the equality. I hate when it does that. Now, do you understand how to find these assumptions? You will see more problems in the next test, and actually I have also some problems that I would like you to watch also. Finally, I will solve a problem. I will say a few things about problem number 1, the solution of problem number 1. So I'm closing this. We had the 200 women and the 200 men, and you remember that we have a confidence interval 5 plus minus 0.4, and we want, this was mistakenly calculated. That was the homework problem because the investigator paired the observations, but they are not paired as we argued. They are observations from two independent random variables x and y, because the group of men and the group of women are assumed to be independent. So what would be now if we make the correct interval? Well, let's see. That is actually something very interesting, and we need to explore it. So I'm going here again to my let's do a new. That's very quick. So we have x and y independent random variables from y, and x is resting pulse of men, y is resting pulse of women. And we assume that these are independent, and what we want to test is we want to estimate the difference of the two means. Well, regardless of what these are, this is the difference of the mean of the difference of x minus y. But x minus y are independent random variables. So what we have here should be the following. This is what should have been used. Let's look at the variance of x minus y. The variance of x minus y is, this is exactly what he estimated. This is sigma, this is s. This is approximated by S of S square of D, where D, when we pair the samples, is the difference between the pulses of one man from one woman. And you select the man and the woman in the way you pair the observations. Okay, so now you have this pairing. So this quantity is approximately equal to this because we have very big samples, 200 individuals of each side. So D, we have a sample of D, of values of D, which has size of 200. So we'll use this value. The test we would be using, since we have a sample value, a sample size of 200, is actually the same, it would be the Z, so we will use Z to estimate. So we'll take xy minus y bar minus Z of alpha over 2 times S of D divided by the square root of n. That's what he used. That's what he did by pairing the observations. But the variance of x minus y is the variance of x plus the variance of y. And since x minus x and y are independent, then the measurements that come from them, and hence the average, the sample averages, are also independent random variables. Whatever statistics you produce from independent random variables are themselves independent. So the variance of x bar minus the variance of D, which is the variance of x bar minus y bar, which is equal to the variance of x bar minus y bar, those are sample averages, is equal to the variance of x bar because of independence plus the variance of y bar. But each one of them is equal to sigma of x squared divided by the square root of n plus sigma of y squared divided by the square root of n. Which is the thing, what I should have put. The correct interval is this. And since you don't know the values of the sigmas, you replace them with the values of the sample standard deviations. But here you don't need to do anything because you already did the calculation. The problem did the calculation for you. You just have to think a little bit. Now, this quantity is equal to this quantity. And this quantity is equal to this particular quantity, which is sigma, which is SD squared divided by N. So, in short, what I needed to know, and I didn't have, is already calculated. Is approximately equal. Here, a very big contribution to making this valid is that you have 200 men and 200 women. You have equal sample sizes, because otherwise this wouldn't be correct. But if you didn't have equal sample sizes, the investigator would not have been able to do the stupid mistake to pair the observations, to pair the independent observations. So in short, what he calculated here, which is this, the approximately equal, this is the 0.4 that is given, so this quantity that you needed to do is 0.4. So in short, the confidence interval remains unchanged even when you do the correct calculation. That's the answer to the problem.